Hello, everyone, and welcome to the AIM webinar series. AIM is the global industry alliance for stakeholders of RFID, barcoding, and smart devices, and other automatic identification and data capture technologies, and supporting blockchain, IoT, and RTLS applications. Our stakeholders include manufacturers, software vendors, distributors, integrators, resellers, governments, and end users across all industries who depend on accurate, available, and identifiable data. AIM creates standards, promotes community, advocates, and educates, enabling adoption, growth, and interoperability to those who depend on accurate, available, and identifiable data. AIM membership gives you the opportunity to influence the direction of the industry. As a member, you receive early access to industry technical research and information. Most importantly, you gain access to a worldwide network of industry leaders and decision makers to promote and effectively use AIDC technologies. Before we get started, I did want to review some housekeeping slides. First is our antitrust policy. It's the policy of AIM to conduct its operations in strict compliance with the antitrust laws. No AIM activity shall create even the appearance of a violation of the letter or spirit of the antitrust laws. Next is our collaboration and work product policy. AIM committee meetings and presentations like today's are held for the primary purpose of advancements in our industry, which necessarily involves development of work product intended solely for the public domain. AIM's developed this policy for the protection of its members who engage in this important collaborative effort. Also, I wanted the audience to take note that you are muted throughout the presentation, but if you do have questions for our presenters, you can send those by using the Q&A dialog box at the bottom of the screen. We'll try to answer as many questions as we can. Today, I'm here with two experts from Spotsy, Jan van Niekerk, who is Vice President of Engineering and Innovation, and Angela Kerr, the Vice President of Product and Program Management. Today, they will be giving an overview of the physics of supply chain impact damage events and the role of RFID in detecting it. Angela, take it away.
Thank you. So I'd like to start out by talking about why this is even an important topic. In today's supply chain, product mishandling is a concern for many companies. In fact, it accounts for 2% of shipments are reportedly damaged during transport. Doesn't seem like a very large percentage, but when you place that into context, that accounts for $2.3 trillion annually. And if that financial pain wasn't enough, there are extra hassles associated from shipping damage. So first, your brand takes a hit when your product arrived damaged. It doesn't matter if the product was fine when it left your dock, the customer is left with a taste of the product didn't work. So they're disappointed in the product, and the product now has to be replaced. Now the customer has a decision. Are they going to replace it with your product, or are they going to turn to a competitor to replace it because they have a perceived quality issue? Then there's the return logistics that have to be managed. So getting damaged product returned for repair, shipping new product out, managing all the inventory implications of that, all come with costs. Then there's the waste and environmental impact. So if the product is damaged beyond repair, if it can't be repaired, does it just end up in the trash, contributing to, a global waste problem? So what options does a company have? Well, one possibility is you increase the packaging, but as with any choice, there are also consequences that go along with that. Extra packaging means adding extra cost to the packaging. It also means that you need more space to store more packaging, and space comes at a price. So now you have a larger, heavier package, so transportation costs are higher. And you have more packaging, and now you have more of an environmental impact again because you have to dispose of that packaging. And that all comes in an age when everyone is trying to reduce packaging, so adding more is probably not the best alternative. So what choice do you have? Well, deploying a monitoring program might be the solution to address your damage issue. By simply adding an impact indicator, we've had customers see as much as a 50% reduction in their damage rates. These devices change the behaviors of supply chain handlers. So now Jan is going to discuss the physics behind supply chain damage with a simple ball spring model. He's going to represent a product and the forces acting on it, and the model will be used to explain how products are damaged and how indicators can monitor for the same damaging forces on the outside of a package. Jan?
Thank you, Angela, and welcome everyone. My name is Jan van Niekerk. I'm the VP of Engineering for Spatie. And as Angela said, we're going to start with a very simple model where you can imagine a box with your valuable product dropping to the ground because, it slipped out of somebody's hands or it was thrown from, the dock door of a distribution center, or whatever the reason is. But in the picture here, there you see number one, a box dropping to the ground. And the model for our product inside is a simple spring and a ball. And what that spring and ball represents is really the forces that hold your product together and ensure that it retains its value and physical form. And the weight one there is essentially the residual weight of the product itself. And our journey is going to start in figure 2 or part 2 there. And that is when the box actually hits the ground. And in this case, you can think of the fixing point of the spring, the top part of the spring where it's held to the box, at that point being fixed in space, being tied to something, in this case, the frame of the box. The box has now stopped, but the ball, the weight is continuing down because it has momentum. And what's going to happen now is it's going to start stretching that spring. And that spring really represents all the forces that hold together and make up the physical properties of your product. And we're going to look at this very simple model of the ball and the spring and its behavior, come to some very interesting and exciting conclusions on that, and then show how that ultimately ties through to what we can do with RFID to take a look at what's happening inside that box without really opening the box. So since we're talking about a ball and a spring, we're going to start with a small spring primer just to make sure that we all understand why we're using a spring. But before that, I just want to say, even though the spring is what's typically used in physics handbooks, I think it's probably clearer when we think about a box falling as the packaging at the bottom that's really stopping the fall. Like, think of it as the weight falling onto a sponge that's preventing it from breaking. And in that case, the sponge would get compressed, but ultimately that's really just another model of the spring. So in that case, if the sponge is at the bottom or the packaging material of your box is at the bottom, is going to get compressed and in that way absorb the energy. But once again, we can model all of that simply with a spring. And so in the case where you're thinking of polystyrene or a sponge that help protect your product, once again, by flipping it over and fixing it on the top, the model of the spring is essentially identical. So since this is the typical physics textbook way that such an elastic system is handled, we're going to do a spring primer. What you see on this slide 4 is essentially a graph. And when you look at a graph, you always have to understand what's the horizontal and vertical axis. So in this case, our horizontal axis, as you can see there, is length. For people in the US, that would be, say, in feet. And for our more sophisticated ISO countries and listeners, that would be meters. And the force on the left-hand side there, typically something like newtons or, depending on what units you want to work in. Now, the red graph there, which is actually a plot on the graph, is just an example of what the force is that you would have to extend to actually stretch that spring. And you can see on the left-hand side, when there's virtually no force, the spring is not extended at all. So the length of the spring does not increase from 0. In the middle is the spring slightly extended, and you can see we need slightly more force. And then at the end, the spring is well extended and we need more force. The more important thing here is that the force that's needed is a straight line function. So in other words, when you put force on a spring and you extend that spring, the force required for a certain extension is a linear function, and you can see the formula at the bottom. The force on the spring is K times the length. So the longer you make the spring, the longer you pull the spring, the more force you need, but it's a straight line function. And that K factor in there is called the stiffness of the spring, and it typically has units of force per length. Now, one of the things that we have to think about is we're talking about supply chain damage and damage to your products. So we also have to consider that these springs and the model that we have will be of a breaking spring. So what happens at that point is if we extend the spring beyond what it can endure, something changes. It not really becomes a spring anymore. And at that point, as you can see on the graph, the spring forces disappear. They go back to 0, and essentially the spring function is terminated. But that is the point of damage in your product. So the simple takeaway from this is at the point where in our model the spring breaks, which is at a certain force threshold, then the function of the spring, i.e. holding everything together, keeping the shape of your product, essentially vanishes. What happens in practice is typically the metals or the plastics, the polymers that make up the physical structure of your product cannot withstand those forces, and the intermolecular forces give way and the product essentially shatters. So this is the model for that. But once again, just part of a spring. So we know 2 things about a spring now. It's got a linear force to length function, and the spring will break at some point, and that is how we model damage in our product. So one final thing about springs is that springs can have different stiffnesses. So we can have a weak spring, which in this case would be K1. And what that means is you just need less force to extend that spring a certain length. And when you look at K2, you can clearly see that would be the stiffer spring because we're going to have to pull harder. In other words, exert more force to get to a certain length. So the real point here is that we find and can manufacture springs in different stiffnesses, and they require different forces for different extensions. So that's enough about springs. So now we can go back to our ball and spring model. So in this case, we've removed the box. Remember, the box frame has now touched the ground, and the model is just that the top point of the spring is now fixed, and the red arrow below 1 means that that ball wants to continue going down at the velocity that it was when the frame hit the ground and when the top point was fixed. And we can kind of, in our minds, imagine what's going to happen in the next few fractions of a second. And that's the pictures there from 1, 2, 3, 4, 5. So as the ball continues down, it's going to start extending that spring. And by virtue of what we just learned about springs is that spring is going to start exerting a force on the ball. It's going to start pulling back. When we get to point number 3, that spring is now well extended and a large force is being exercised upon the ball. This is going to slow down the ball. There's going to be a point where the ball actually stops. So it's going to have less velocity, and we're going to see, this in much more detail in the slides that follow. But this is just the oversight, the overview of the entire process. And then the spring is going to start pulling, but the ball is going to start moving in the opposite direction. And when we get to 0.5 in our model, we're not considering losses. So at this point, where we get to where the forces on the spring is 0 again, in other words, the length of the spring has returned to the original length in number 1, the ball is now going to be moving in the opposite direction. So you can think of this as, the ball falling on a trampoline, going down, ultimately stopping, and then bouncing back. Just in this case, the trampoline is not the spring underneath it, but the spring above it. But that's the model. And that's what we call the first half cycle of that impact event. And we're going to call it a half sign later on, and you will see why. So once again, we just want to think about the damage part of that and why things break. And the reason things break is that the forces that keep them together are exceeded, and we get typically damage on the molecular level. Those ionic or covalent bonds of your plastic or metal shear and shatter, and the spring simply doesn't function as a spring anymore. Your product loses its shape, loses its value, and has to be returned and repaired, and all those bad things that Angela mentioned. So here, just a slide to see, as we extend that spring, we get to a point where the spring forces are exceeded, the spring shatters, the force that the spring can exert back goes to 0, and the product loses its value. So that's enough about springs, and now we're going to look at some of the basic physics of motion of our ball and spring model. And this is a classic first year physics. So if you're in a technical field and you had physics 101, this was typically one of the models that you did in your first year. And we're going to look at 4 aspects of it, namely position, speed, acceleration, and duration. So we're just going to define what each of these are. And the first point is position. So every item in the supply chain has a position in free space that we can measure relative to a reference point and let's say use the units of feet and meter. And then next, we have the speed or the velocity of the device, which is really the rate at which position changes. And we're going to simplify this to a one-dimensional problem to make it as simple as possible to solve. And here's just an example. If a position changes 10 miles in 1 hour, the speed is 10 miles per hour, or we can do the metric thing and say if your box position changes 10 meters in 1 second, somebody drops it from the dock door, then the average speed would be 10 meters per second. So very simple, and going back to high school and college physics. So next slide, please. So here's a drawing of what happens with a spring. And once again, the basic picture that you see here is a graph. So on the horizontal axis is time. On the vertical axis, which is not shown here, by the way, vertical axis is taken out just to make it a little more clear. But the vertical axis is position. And the green line there is showing the position of an ideal ball and spring model over time. And, we've already gone through this, but what you can see, what is happening is in 1, the ball, the spring is just fixed, so there's no force on the spring. This is when the box just hits the ground, right? And we affix the top part of the spring in space. The spring is now starting to extend and exerting a force. The ball still goes down, but at 3, all the velocity is taken out of the ball. The ball is for a fraction of a second there in a standstill position. And then the ball starts to bounce back in 4. And when we get to 5, the ball is, full speed going back in the opposite direction of which it came from. So that's the first half cycle of the impact event. And if you've done this in college, you know that this is actually a harmonic motion. So if you can think of this spring as an ideal spring which can be compressed the other way, then this would result in an harmonic sinusoidal oscillation of the ball and the spring, as it in time. But we're really only interested in this first half cycle. So we looked at the position there, and here it's shown, as a dotted line, the green position. But when you go look at that analytically, when you solve these equations, you find that that is a half sine wave, an inverted half sine for the position. In this graph, we look at the speed, and if you did college physics, you'll know that the speed is just the time derivative of that of the green curve of the position, and that turns out to be sinusoidal as well. In this case, it's a cosine, and it's literally just the time derivative of the position. But let's look at it. So in this graph, which again, the horizontal axis is time and the vertical axis is speed, and the graph that we're looking at is the red graph, you can see that the ball starts with a high speed, and then as the spring starts pulling on the ball is slowed down. And when we get to 3 there, you can see that the red speed graph actually crosses the axis, which means right at that point, for that moment, the ball has come to a standstill, and then speed goes under the line, which means a negative value, which really means it's changed direction, and the ball's now going back. And what you can see at 5 is the speed at which the ball came in at 0.5 is the speed that the ball is going up at that point in time. So the ball has come in, slow down to a standstill right in the middle, and now it's going back. So in that first half cycle, of which you can still see the position there, the speed half cycle goes from full speed in to standstill to full speed out. So that's the first two, namely, speed and position. And we're also going to look at acceleration. So let's just think a little bit about what acceleration is. It's the rate at which the speed changes. So here's an example. We have a box falling off a forklift. And at the point where the box falls off the forklift, we define that as 0 meters per second. And the box starts falling down. And 1 second later, the box is traveling at 10 meters per second. So the change in speed from that of that box over that second is 10 minus 0, because it started at 0. So the delta, or the change, is 10 meters per second. And how long did it take for this change to happen? 1 second. So therefore, the acceleration is the change in time, which is 10 meters per second, divided by the time, which is also 1 second. So 10 meters per second, or sometimes this is written as 10 meters per second squared, because it's meters per second per second. So that's the very basic physics of acceleration. And so on the next slide, please. We have a graph where we plot all 3 of those parameters or phenomena, namely the position, which we are now familiar with, of the weight, the speed, which I'm now showing in a dotted line, and the acceleration. And the acceleration, once again, is just the time derivative of the velocity. And as you can see, it really depicts the change in velocity, and you can see where the acceleration is maximum, which is right there in the center of the curve, is where the speed is 0. But you can also see that that's where speed is changing the most, because you have to look at the slope of the speed graph to understand where the biggest change in speed or velocity is happening. So here you see a graph that's got both the acceleration, the position, and the velocity of the ball for the first half cycle. And this is really the only model that we need to get a good grip on the fundamentals of supply chain damage. So this is one of the fascinating aspects of this model, and you'll see fundamentally this insight is really what Spotsy has built an entire product range on. Is that the big insight is that the duration of the acceleration has nothing to do with the velocity, the incoming velocity, or the drop height of the box. It only has to do with the relationship between the mass and the stiffness of the spring. Now, that doesn't sound too impressive when you first think about it, but I'm going to talk a lot more about this, and we'll see what the conclusion is on this. But this is really fundamental to supply chain damage and making supply chain damage visible. So the 3.14 there is not really 3.14; it's the constant pi. But it so turns out that the duration, in other words, that the time that it takes for that acceleration to get back to zero after the impact, is only determined by the square root of the ratio of the mass of the ball and the stiffness of the spring. So just let that sink in for a second, because that's a really important conclusion. So remember, we're talking about acceleration here and the duration of acceleration. So knowing that that duration is fixed, what is really happening when I drop the box from different heights? So the point is that the only thing that really changes is how you can phrase it many ways, but how far the spring is extended is one way of saying it. How far the weight would go down is another way of saying it. And what is the magnitude of the acceleration is just another way of saying exactly the same thing, because remember, from our previous pictures, the acceleration is really just the positive half sign of a position. So the point is there, these examples 1, 2, and 3 would be examples of different velocities that the weight has when the spring point is fixed in space, which really just means drop heights for the box. And we'll see more of that in the next slide. So if you think back on what we just saw in the previous slide, where you can say that there are different extensions, when you go draw that out on a graph. So once again, this is a graph. What's on the horizontal axis? The height at which the box is dropped. And on the vertical axis is how far the spring would extend for a given spring stiffness and weight. And you can see that that is a quadratic function. And I tried to put the formula at the bottom there that says the spring extension is some constant times the square of the height. And that square is encircled in red because that means that it's a quadratic effect that drop height has on product damage, right? So when we get to a certain extension, the product breaks. And as you can see, if I drop the box from a meter, let's say that spring is going to extend 1 centimeter. But if I drop that from 2 meters, in other words, if I double the drop height because of the square there, the spring is not going to be extended 2 centimeters, but 4 centimeters, because it's a square function. So there's a really important conclusion from this, and that is that drop height of a box has a phenomenal quadratic effect on the probability of damage. So as you can see, as that spring is extended more and more, the probability of damage is just extended. So we all know this, but it does bring home a very important point, is that if you minimize the height at which your products are dropped, then you definitely significantly reducing risk of breakage. But the important point is that it's actually the square root of the drop height that has an effect. So it's really important, as you plan supply chain handling of boxes and your products and materials, that you think about how to minimize that drop height. So here's some of the insight that Spotsy uses to show what's going on inside a box, and it all boils down to what we have just seen, where we say that the duration of that half sign acceleration pulse is a function of only the mass and the spring stiffness. So if we have a certain box that we model, and we can come up with another tiny little box that has a different mass and a different spring stiffness, but which has the same ratio to mass and spring stiffness as our box, then the time behavior would be absolutely identical to that of the big box. So we can build a model box of our actual supply chain goods, and by choosing the right mass and the right spring stiffness, we can emulate the time behavior of the actual box. And by doing that, we really make our small box a scale model of the big guy. And that's really the very important conclusion. The one thing that you can walk away with from this presentation is that by choosing a right mass to spring ratio, you can mimic the behavior of what's going on in a box in the supply chain. So once again, a reminder that when we want to emulate damage, we have to emulate a breakage of the spring. So when we build a tiny model of what's going on in our box with a different spring, remember we're saying that we want to have the spring and the mass and the mass and the spring stiffness in the correct ratio to emulate our goods. We also have to emulate the breakage of the large box in our tinier spring. So we have three things to emulate: the mass, the spring, and the point of breakage. But if we do that right, then our tiny box behaves exactly like the big box. So this is an example, once again, just a point that the duration is only a function of mass and spring stiffness ratio. And again, the concept there of having an actual box with a mass and a spring stiffness, and an emulating box with a mass and a spring stiffness. And in this case, I'm basically showing you one of Spotsy's product called a shock dot, where we really do that. And this is just a tiny plastic cup that you can actually see in the center of the sticker over there. And the mass in this case is literally just a drop of red ink that is held in the cavity in the plastic dot there, literally by capillary forces. In other words, the suction forces between the plastic cup and the drop of ink. So it doesn't look like it, but ultimately the mass of that unit is the mass of that drop of ink. And the spring in this case is the capillary forces between the drop of ink and the plastic cup. But since those are in a specific ratio, we can choose those ratios to represent typical mass and spring ratios that is found in the supply chain. And therefore, we can come up with an extremely simple emulation of what's going to happen inside your box in a low-cost plastic cup that you can stick on the outside of a box that will indicate events that are very similar to what the inside of your product is going to go through. So that's really the basis of making something that is a model of what's going to happen inside your box. So I just want to talk about visibility, accountability, and behavior. You see these videos of, the airport handlers throwing the boxes around, and people go, how could these people do this? And I often think about, when we take our fragile products and we hide them inside a box, we're really taking away the ability for a handler to understand and see, that your product is fragile inside. And what we do is when we add something like an indicator on the outside, we're not only providing a way that we keep these guys accountable and we can punish them if they do this. What we're really doing is we're sharing the events that are going on inside the box on the outside, and in that way we're making handlers partners with what's happening. He can see a simulation of the inside world of that box, which was hidden to him when we put all the packaging material on the outside, in a little world on the outside that is completely visible. And I believe that's one of the reasons why, when we add these impact indicators to a program, that you immediately see handling, reduced by 50%. And I've seen this personally, dropping off, a package at FedEx and our indicators on the outside. And, the FedEx guy says, is this thing active? And I'm going, oh yeah, it's monitoring for high impact. And you can see at that point, the box is just handled differently. And just to make another point here, the half sign curves for our technical data sheets, because the engineers that design packaging is very interested in this, is available for some of our products. So here's another example of a ball and spring indicator. Now, in this case, you can see that's not a spiral spring, and it's definitely not a ball. But that rectangle, that red rectangle here, is really our ball. We call it a proof weight. And on the left-hand side, you can see that when that proof weight moves to the bottom, then it shows through a window and it provides warning and insight that the breakage event is happened. And in this case, the spring are those two little blades that you see at this point kind of curved downwards. And normally they hold the proof weight, the ball, in the middle between the two windows. But when a certain force is exceeded, they also have a linear force curve, but they are designed in such a way that when a certain force is exceeded, they change shape, which is really emulating the snapping of the spring. And at that point, instead of pulling back like a normal spring would do, because of the change in shape, they actually start pulling, and they ensure that the weight snaps to the top or the bottom, and therefore permanently remembers, without a battery of any kind, the event that has happened. And of course, to add RFID to this is fairly simple. Go to the next slide, please. Adding RFID to this, as you can see there on the bottom right-hand side, we take our emulator, which is in that case the ShockWatch device that you've just seen, and we simply add a contact switch to open or close when that weight, when the spring breaks and the weight is moves completely out of behavior. So this is exactly what happens in the slide that we just previously seen. We take an RFID back, we add that to our detector, and then all of a sudden you have a device where, on the left hand side, you have your product with a certain mass spring ratio. We have our detector on the outside with the exact same mass spring ratio. But in this case, when that damage happens, we trigger an RFID circuit, and you can go, do standard ISO 18006 RAIN RFID memory location access to actually find out whether that event has actually happened. And on the left-hand side there, you see the 4 lines of code that we, for instance, add to an impinged reader to be able to read the contents of what we call the damaged bit in the RFID chip. And that's all from me. So I'm handing it back to Angela. The conclusion here is, by very basic spring physics, allow us to emulate what's going on inside the box. And we can use that to really detect and deter damage in the supply chain.
And I think with that, I think Jan's summarized us up pretty well. The one other comment is that, the most important thing is supply chain damage isn't something that you just have to associate as just another cost of doing business. There are alternatives for you. And, integrating low cost indication with RFID really allows you to automate your supply chain processes and find this damage, possibly even prevent this damage before it even happens.
Okay, great. Thank you for your time and information today. We still have time for questions. If people have any, they can send them via the question and answer box at the bottom of the screen. But I will go ahead with our first question if you two are ready.
Go
Absolutely.
ahead.
Great. First question we have is, will the impact be recorded if it occurred between two RFID scan points?
So the way these indicators work is they're not real-time communication. So you would scan the RFID at one point, and you would know that, as it was leaving that point, it was fine. And then when it arrived at its next point, it would show that you'd had a potentially damaging impact, and that you needed to take action at that point. So you would know you'd know something happened between points, but you wouldn't know exactly where.
Yeah, I would say, if you think about the ball and spring model, the indicator is always on, right? The spring will always break when the impact event happens, and we know that the spring is broken. So when we get to the RFID scan point and we scan the device, we report that the spring is broken. Now, obviously, if you're between two scan points, the cost of this product and the way that it was designed, it doesn't have a battery, it doesn't record the time of impact. So the way that you do this and the way that you get to the cost point that is necessary to ensure that this is on, even the lowest value packages, is that you do it, you keep the indicator on always, but you do scan points, because typically at scan points is where the responsibility of handling changes. So there's an incoming party that says, I delivered a good product, and then a receiving party that say, I received a product that doesn't show any impact damage. So between scan points is the answer.
Okay, great. Thank you for that. Another question we have is, how do you choose the correct acceleration value?
Yeah, as you can see from the model, what you have to do is you have to choose the right spring to mass ratio. But we've sold the RFID list indicators for decades, so we have a lot of experience, and we sell them to thousands of customers all over the world. So we have a whole series of them, but there's typical accelerations that very well cover what's going on in the supply chain, and they come in denominations of 5G, 15G, 25G, up to 100G. And when you go look on our website, there are, for instance, tables that guide you. If you know what the volume and the weight of your package is, that will give you good guidance to figure out what indicator or what G level indicator you should choose to put on your package.
Okay, thank you for that. Another question we have is, can Shockwatch RFID be reused?
So it is a single-use device. So once it's affixed to a product, it can stay with that shipment, but it cannot be reset. And that really is important, because we don't want anybody in the supply chain to be able to tamper with the device.
And that also brings up an important point is when you look at the device itself, when you remove the sticker to put it onto a package, there is automatic arming. So in other words, there's a pin that holds the proof weight in the centered position, so that when we ship these indicators to you and somebody drops the package with the indicators in, then they don't all go off, right? So they stay primed until you remove the back label to put them on a package. And right at that point, as you pull out the back label, you really pull out the arming pin and the device becomes live and sensitive to impacts. So one of the reasons why you don't want to do that is that once you start taking them off and handling them, there's a chance that you can trigger them because at that point, when they're not attached to a package, they can very easily experience the accelerations that would trigger them.
Okay, great. Another question we received is what type of, I guess, packaged products have typically been used that you've seen? Has it been mostly electronics?
So we've been involved in all sorts of industries with these sorts of things. So it's been electronics, it's been, oil and gas tools, it's been, automotive parts, glass and mirrors, furniture. I mean, honestly, if anything is fragile, and susceptible to damage in the supply chain, this is an alternative for those customers.
Okay, great. Looks like that is all the questions we have for today. I actually do have another question that someone wants to take offline that I'll send over to you guys. But once again, Jan and Angela, thank you so much for your time and your insights today. Greatly appreciate it.
My pleasure.
Thank you, Michael, and thank you for everyone for attending.
And I want to thank again the audience for their participation today. Appreciate it. Thanks, everyone, and enjoy the rest of your day.